The first speaker of this session will be Y.Sato from Nagoya University, and he will talk about two-dimensional causal dynamical triangulations, and two-dimensional Horava-Lifshitz quantum gravity. Please go ahead.
Oh, hello. Thank you very much for the introduction. First of all, I would like to thank the organizers for inviting me to this nice conference. Today's talk is about the relationship between the two different models of quantum gravities in two space-time dimensions. And the one is a lattice quantum gravity called causal dynamical triangulations, dubbed CDT, and another one is a certain version of the Horava-Lifshitz quantum gravity in two dimensions. It is known that these two models are equivalent in a sense that they produce exactly the same physics. In this talk, in particular, I wish to discuss what happens to this relationship if we include wormholes and the baby universes in a non-perturbative manner. And also, I wish to show you that the so-called the Coleman mechanism works in some sense. All right. So this talk will be based on my recent works with Yanan Byon, Yoshiyuki Watabiki, Yuki Hiraga, and Yoshiyasu Ito. And if you have questions, please stop and ask me anytime. All right. Okay, so before going into the detail, let me briefly explain a lattice quantum gravity called dynamical triangulations. And 2D dynamical triangulation is a sort of way to regularize the random surfaces. There are two kinds. The first one is the Euclidean dynamical triangulations called EDT, and another one is the causal dynamical triangulations dubbed CDT. In EDT, one discretizes the surface with the Euclidean signature based on equilateral triangles like this. On the other hand, in CDT, we discretize the foliated surface with the Lorentzian signature based on a very special kind of triangles like this. And both in EDT and CDT, we fix the length of each triangle. So to introduce the randomness or to quantize this system, we have to take a sum over all possible ways of gluing of these triangles, the triangulations. And here, each triangle serves as a UV cutoff. So in order to read off the physical quantities out of this system, we have to remove it in the end of the day. And this can be done by the process called continuum limit. So if you take the continuum limit, this EDT becomes the Liouville quantum gravity that is invariant under the full diffeomorphism. On the other hand, in the CDT, if you take the continuum limit, we have the two-dimensional projectable version of the Horava-Lifshitz quantum gravity. That is invariant only under the subclass of the diffeomorphism that keeps the foliation structure. Okay, and in this talk, I would focus on the second case, CDT versus the projectable Horava-Lifshitz gravity. In the original setup of the CDT, the creation of baby universes and wormholes is prohibited, so they are not allowed to occur. However, we can relax this condition and generalize the CDT in such a way as to include baby universes and wormholes in keeping with the foliation structures. And here, the baby universe means the universe that branches off from the mother and vanishes into the vacuum. And the wormhole is a sort of handle in this talk. And the somewhat amazing thing is that we can take in this kind of, well, all possible wormholes in the baby universes in a non-perturbative manner. Okay, and then the questions we asked in this study are the following. So now we know that the quantum limits of the CDT is the projectable Horava-Lifshitz gravity. And then what kind of interaction should be introduced to this 2D projectable Horava-Lifshitz gravity to reproduce the baby universes and the wormholes? This is the first question. And the second one is that does the Coleman mechanism work in this setup? The very roughly speaking, Coleman mechanism means that if we take a sum over all possible wormholes in the context of quantum gravity, the cosmological constant is not important. And in fact, this Coleman mechanism really works in this setup in some sense, but in a manner different from what Coleman originally had in mind, I think. Okay, so here is the contents of my talk. First, I will review the CDT and the Horava-Lifshitz gravity and explain the relationship between them. And then now I will explain how to introduce the wormholes in the CDT setup based on some techniques called matrix models and string field theories. Then I will show you that the Coleman mechanism works in some sense. And in the section 4, I will show that what kind of interaction should be introduced the Horava-Lifshitz gravity to reproduce the CDT with the wormholes and baby universes. And then I would summarize my talk. Okay, the first section is the CDT and the Horava-Lifshitz gravity. So first, let me explain what CDT is. The starting point is a two-dimensional globally hyperbolic manifold. So that has the global time foliation. It means that each leaf of this foliation is a Cauchy surface, so they do not touch each other. So this is the setup. And in the CDT, we discretize this foliated spacetime based on a very special kind of triangles that has space-like and time-like edges. And they are called space-like and time-like because if you take the square of the lattice spacing for the space-like edge, we have the positive signature. On the other hand, for the time-like edge, we have the negative, and here alpha is a positive parameter. Okay, and to quantize this system, we implement the path integral. The path integral of the quantum gravity is that we fix the initial and the final geometries and take a sum of all possible histories in between. And in the discrete setup, we fixed the length of the initial and the final boundaries, say L1 and L2, and take a sum of all possible histories. And this can be done by taking a sum over all possible triangulations. Take a sum of all possible ways of gluing triangles. Okay, and here SR is the lattice action called the Regge action. So let me introduce this Regge action. Okay, so in the CDT, we fix the topology. So the important action is the cosmological constant term, this one. And in the discrete setup, we replace this bare cosmological constant, lambda naught, by the dimensionless cosmological constant mu over the lattice spacing squared. And this part is the area of the surface. So in the discrete setup, it is equivalent to the area of the triangles times the number of the triangles. So this is the discrete area. Okay, this is the Regge action. This is the starting point of the lattice quantum gravity. And for simplicity, usually we rotate to the Euclidean signature. And this can be done just by replacing this alpha by the minus alpha. Please look at these equations. So if you replace alpha by the minus alpha, this time-like edge becomes the space-like edge. So in this sense, it is called the rotation to the Euclidean signature. So if you do that, we have the Euclidean Regge action. Now this parameter alpha can be absorbed into this mu, the cosmological constant, and then we end up with the very simple form. The cosmological constant times the number of the triangles. So this is the Regge action. So using this Regge action, we can define the path integral of the CDT. This is the propagator. And in fact, if you use some combinatorics, you can evaluate this in an analytic manner, at least in the 2 dimensions. Okay, and in order to read off the physical quantities out of this path integral, as I have said, we have to take the continuum limit such that we tune the cosmological constant to its critical value, mu c, and simultaneously we take the epsilon to 0, the lattice spacing to 0, with the renormalized cosmological constant kept fixed. The physical reason behind this procedure is that if we tune this mu to its critical value, the average number of the triangles blows up. And if simultaneously you tune the lattice spacing to 0, then you get the continuum surface. And also the information of the lattice spacing can be transmuted into the renormalized cosmological constant lambda. This is a sort of dimensional transmutation. Okay, anyway, if you take this continuum limit, you can get the renormalized propagator or the amplitude. And this renormalized amplitude satisfies this differential equation. And this H naught is the Hamiltonian. And this is Hermitian with this measure. So let me summarize what I have explained so far. CDT is a lattice quantum gravity. And to get the physical quantities, you have to take the quantum limit. If you do that, the physics can be expressed by the quantum mechanics of the one-dimensional universe with the length L that propagates in time with this Hamiltonian. So this is the quantum limit of CDT. So from now on, I will explain if you quantize the projectable Horava-Lifshitz gravity, we can get this exactly, this Hamiltonian. Okay, so let's move on to the Horava-Lifshitz gravity. So we start with the 1+1 decomposition of the 2D Lorentzian metric. So in this ADM decomposition, we have the spatial hypersurface, this, and also we have the time direction sticking out of this hypersurface, and its normal and tangential direction to the hypersurface can be quantified by the lapse and the shift functions. And this H11 is the induced metric on this hypersurface. Okay, and if the system has the full diffeomorphism, Of course, you can change the shape of this hypersurface as you wish. So it means that this foliation is just a gauge artifact. However, if the system only has the foliation preserving diffeomorphisms, um, you cannot change the shape of the hypersurface. It means that the system has the intrinsic hypersurface structures. Okay. And the Horava-Lifshitz gravity is a gravitation theory that is invariant under this foliation preserving diffeomorphisms. And in particular, in 2 dimensions, we have this classical action. And this lambda tilde is the cosmological constant, dimension full. And this eta is a dimensionless parameter. And also kappa is the dimensionless Newton constant, gravitational constant. And this k is the trace of the extrinsic curvature. So this is the Horava-Lifshitz gravity in 2 dimensions. But in particular, we consider the projectable case such that this lapse function is just a function of time. Actually, this is the consistent truncation of this Horava-Lifshitz theory, because if you transform this lapse function using the foliation preserving diffeomorphism, and then this lapse function remains as a function of time. So this is a consistent truncation. So from now on, we just think about the projectable Horava-Lifshitz gravity. Okay. And this Horava-Lifshitz theory is a sort of constraint system. And so there are some constraints. And we first solve the momentum constraint at the classical level. And this momentum constraint corresponds to some generator of the spatial diffeomorphism. So if you solve this momentum constraint, the physics can be described by the gauge invariant quantities. And L is the invariant length of the 1D universe, and T is the proper time. And the important point here is that this proper time is invariant under the foliation preserving diffeomorphisms. So this proper time is gauge invariant. So using these invariant quantities, it makes sense to compute the amplitude or the propagator, starting with the universe with length L that propagates in time, and end up with the 1D universe with the length L prime. And this can be expressed by the path integral. For simplicity, computational simplicity, we fix the lapse function to be 1. But the corresponding ghost, it is decoupled from the dynamics of the L, so we just ignore it. And we move on to the Euclidean signature. Then this is the Euclidean action. Okay, and the lambda here is related to the cosmological constant, lambda tilde. And in principle, this can be positive, negative, and 0. But to get the CDT result, this lambda should be positive. So from now, I will stick to the positive lambda. Okay. So from now, I try to read off the quantum Hamiltonian from this path integral. Let me show you how to do this. So we introduced a function psi, which is defined by this bracket notation. And this here, epsilon is small. And if you insert this completeness condition right here, you can have this integral expression. This G naught is the propagator, the one-step propagator, which can be expressed by this path integral. Okay, and on the other hand, you can expand this exponential for small epsilon. Then at the order of epsilon, you get the quantum Hamiltonian. So what you have to do is to implement this integral and estimate at the order epsilon. Then you can get the quantum Hamiltonian. Okay, to do this, we have to define the integral measure, d mu. And in this case, there are three possibilities characterized by this A. A can be 0 or plus minus 1. So depending on this integral measure, we can compute this one-step propagator just by discretizing the Euclidean action. Okay, so now we know these quantities. So just plug in these two into the expression, and if we evaluate this integral at the order epsilon, we can read off the quantum Hamiltonian. And depending on the three different measures, we have the three different orderings. In fact, this Hamiltonian coincides with the CDT Hamiltonians. And three different orderings has the geometric meaning. For instance, if we choose this ordering, which means that we think about the open universe. And for the last one, we think about the closed universe. And the middle one is a bit tricky. We introduce some points on the closed universe. The marking point is analogous to introducing the coordinate system on this closed universe, but it's not that important. Okay, but so with this agreement, I can say that the quantum limit of the CDT is the quantized projectable Horava-Lifshitz gravity in 2 dimensions at least. Okay, so now we have the Hamiltonian. Let us consider the eigenvalue problems. And then in this case, we have the discrete eigenvalues and also the square integrable eigenfunctions. And also we can consider the Hartle-Hawking wave function, which is a zero energy sort of eigenfunctions, although it is not square integrable. So, but from this wave function, we can capture some behavior of this system. Anyway, so now we have the square integrable eigenfunctions. We can estimate the size of the universe in this setup, which is determined by the cosmological constant. And also, when the size of the universe is very big, the wave function decays exponentially. Okay, as we have seen, this kind of behavior changes drastically if we include wormholes and baby universes in this setup. Okay, so now let's move on to the section 2. So as I have explained, the CDT can be described by the quantum mechanics of the one-dimensional universe that propagates in time. And to introduce the splitting and joining interactions, that is the wormholes, we have to promote it to the field theory that describes the creation and annihilation of the one-dimensional universe. From now on, I call the 1D universe string. So first, I will introduce a psi dagger that creates a marked closed string. A marking and not marking is not important, but it creates a closed string with the length L. And also psi annihilates a closed string with the length L. And the vacuum is defined by these equations. And the creation and annihilation operators satisfy these commutation relations. And actually, this kind of setup can be fixed by the scaling argument. Okay, so based on this string field, original CDT propagator can be expressed by the second quantized Hamiltonian, this one, given by the sandwiching the first quantized Hamiltonian, as we have seen this one. So if we do this, we can compute the propagator but this is just a free propagator. And we wish to describe the splitting and the joining interactions to get the wormhole or baby universes. And so this is the full second quantized Hamiltonian. And the first term is the free propagator, as we have seen. And the second term means that 1D universe vanishes into the vacuum. And the third one is the splitting interactions of the string. And the last one is the merging interactions of the string. So I put the string coupling GS for the splitting and the joining interactions. And this parameter alpha is just a number. So usually we take alpha to be 1, okay? And so based on this kind of string field theory setup, in general, we can compute this kind of amplitudes. So starting with the m loops that propagates in time, and we end up with the n loops, something like this. And from now, I wish to focus on a multi-loop correlation function. This is a graphical expression. So we start with the say n loops, and that propagates in time, but everything vanishes into the vacuum if t goes to infinity. So this is the multi-loop correlation functions, okay? And this can be computed by the Dyson-Schwinger equation of the string field theory. The meaning of this equation is that, so this multi-loop function should not evolve in time after t goes to infinity. Everything has to vanish into the vacuum. So this is the meaning. But in principle, if you solve this Dyson-Schwinger equation, you can find this multi-loop correlation function. But it is a little bit difficult to solve. But a somewhat amazing thing is that there exists an equivalent matrix model description. This means that some non-perturbative equation called the loop equation in the matrix model has the equivalent information of this Dyson-Schwinger equation in the string field theory. If this parameter alpha in the string field theory is related to the matrix size. Okay, and this alpha appears in this merging interactions. So if you find a genus, you get this factor alpha times GS squared. So this alpha counts the genus. So in this sense, alpha is related to the matrix size. Okay, and the corresponding matrix model is given by this matrix integral, and this M is the n by n Hermitian matrix. Okay, and and here some simplification happens. So if we just consider to take the sum over all possible wormholes or the genus, we can simply take alpha to be 1 because we don't have to count the genus. So if alpha is 1, it means the matrix size is 1. So in this case, the matrix model just becomes the one-dimensional integral. So this is quite simple. So from now, I will choose alpha to be 1. Then we can compute the multi-loop correlation functions with the old genus contribution. So this is the result. And the BI and AI are the Airy functions. And here C is a string coupling measured by the cosmological constant. So this is dimensionless parameter. So this is a full non-perturbative solution. And from this expression, we can see that the multi-loop correlation function can be expressed by the single loop correlation function. This is a little bit amazing. But anyway, So now we focus on the Hartle-Hawking wave function, which is the one loop, single loop function, like this. So, but this has the all possible wormhole effects or the all genius effects. So this is a non-perturbative expression. But here, um, let me just do the asymptotic expansion for the small xi. Xi is the dimensionless string coupling constant. So if you do this, you can see this exponential decay as we have seen for the in the no wormhole case. And the point here is that for any finite order of perturbation, we always see this exponential decay. But in a full non-perturbative expression, we have the drastically different behavior. Okay. So let's move on to the Coleman mechanism in this setup. So now we have obtained the full Hartle-Hawking wave function. And this W naught is the Hartle-Hawking function for the no wormholes. So in this case, just decays exponentially, as we have seen. On the other hand, this W is the full Hartle-Hawking wave function. When the size of the universe is very small, its behavior is close to that of the no wormhole case. However, once the universe becomes big enough, it starts oscillating and it decays with this power. And this decay is governed by the string coupling constant. And actually, this drastic change appears because of the infinitely many wormholes, because for any finite order of perturbation, we observe exponential decay. But if we include all possible wormholes up to infinity, we get this change. So this is a sort of realization of the Coleman mechanism, as I will explain in detail. Okay, so next, let me find out the Hamiltonian, including infinitely many wormholes. So if there is no wormhole, we have this differential equation. This W naught is the Hartle-Hawking wave function, and H naught is the original CDT Hamiltonian. And now, if we include wormholes up to infinity, we have obtained this W, the Hartle-Hawking wave function. And we wish to know this H Hamiltonian that satisfies this equation. All right. And this Hamiltonian can be fixed by the two conditions. The first one is that this W satisfies Airy differential equations, and because W is essentially given by these Airy functions. And secondly, this H becomes H naught, the original one, if we turn off the string coupling constant. Because if you turn off the GS, all splitting and joining interactions vanishes, and what we have is just a free propagator. Okay, by this condition, we can fix the full Hamiltonian. Okay, so note that this is the one body Hamiltonian, but includes all possible wormholes and the baby universe effects effectively. And this effect can be realized as this simple last term, L squared. Okay, and you may think that this Hamiltonian is ill-defined because the potential is not bounded from below. However, this case is special called classical incomplete. I didn't have time to explain, but in this case, although the potential is unbounded from below, we can still have the discrete spectrum as well as the square integrable eigenfunctions. It is a bit amazing, but we have. And the result looks like those of the Hartle-Hawking wave functions. So now we have the square integrable eigenvalues, eigenfunctions. So we can estimate the size of the universe, which is infinite. So on the other hand, where there is no wormhole, the size of the universe is fixed by the cosmological constant. However, if we include wormholes up to infinity, the size becomes quite big. Okay. So from now, I wish to explain this kind of wormhole effects can be realized by the fluctuating cosmological constant. So let's go back to the path integral of the original CDT. So this is the path integral expression of the propagator of the CDT. And this H naught is the Euclidean action. Okay, and this lambda is the cosmological constant. So this expresses just a free propagator. And now we think that this lambda is not a constant, but fluctuates around this lambda following the Gaussian distribution. So it means that we fluctuate this lambda by this nu, and this nu follows the Gaussian distribution. So let's think about this situation. And then this nu is the Gaussian. So you can do this Gaussian integral, and we end up with this expression. And as we have done, so if you discretize the time step, you can read off the quantum Hamiltonian. So in this case, we have this one, and this is equivalent to the CDT Hamiltonian with the infinitely many wormholes. So in this sense, we can say that the sum over all possible wormholes and baby universes can be realized by the cosmological constant that fluctuates in time. So it is not really a constant. So this is quite interesting correspondence. So lastly, let me explain what kind of interaction should be introduced the projectable Horava-Lifshitz gravity to reproduce the CDT with wormholes and baby universes. This is the answer. So this is the classical action, and the first term is just the action for the projectable Horava-Lifshitz gravity, as I have explained. This lambda tilde is the cosmological constant, and the second term is the bilocal as well as space-like wormhole interaction, because this last term means a wormhole connecting the two distant points at the same time. So this is a spatial wormhole. And you may think this last term looks weird, but this term is invariant under the foliation preserving diffeomorphisms. So you can include this into the action. Okay, and following the path integral, you can have the quantum Hamiltonian in this case. So this is the result, and this coincides with the Hamiltonian of the CDT with the wormholes and baby universes. And here, GS, the string coupling, is related to the coupling constant for the bilocal wormhole interactions. Okay, at first sight, you may think this is weird because the wormhole in CDT is not space-like. So, but we can say the following thing may happen. So this bilocal wormhole interaction is an effective wormhole interactions, meaning that, so to get this by local time, we have to integrate out all the lengths of the wormholes. And as a result, we get this by local time. So, but we don't know the full quantum gravity, but we have this effective expression. So if we integrate out all the lengths of the wormholes, and then if the zero length wormhole becomes dominant, then such zero length wormhole can terminate or cut the 1D string into two pieces. And so this induced the splitting and joining interactions. So if this happens, this is totally consistent with the CDT picture. But we haven't proven yet in a qualitative and a quantitative manner. So this is a future work. But okay, so if we use this classical action and if you quantize, then you get this full Hamiltonian. All right. So let me summarize my talk. So in this talk, we have taken sum over all possible wormholes in the original 2D CDT setup. In the original 2D CDT, there is no wormholes in the baby universes. And if you include these effects non-perturbatively, we get this Hartle-Hawking wave functions with these behaviors. So if you do not include wormholes, the Hartle-Hawking wave function just decays exponentially like this. However, if you include wormholes up to infinity, the behavior drastically changes. When the size of the universe is very small, the behavior is very close to that of the no wormhole case. However, if the universe becomes big enough, it starts oscillating like this and decays with this power. And this decay is governed by the string coupling constant, not by the cosmological constant. And this drastic change is caused by infinitely many wormholes because at any finite order of perturbations, we still have this exponential decay. Okay, also we have the square integrable eigenfunctions. Using this, we can estimate the size of the universe. If we do not have wormholes, or if we include finitely many wormholes, the size is fixed by the cosmological constant. On the other hand, if we include all possible wormholes non-perturbatively, the size is very big. So based on these behaviors, we can conclude that the Coleman mechanism in some sense works. And that is, the large universe is independent of the cosmological constant, which is governed by the string coupling constant. And also we have shown that the sum over wormholes, this kind of effect can be expressed by the cosmological constant, but that fluctuates in time. Okay, and also this kind of CDT with the infinitely many wormholes can be obtained if you quantize the 2D projectable Horava-Lifshitz gravity with the wormhole interactions. If you quantize this system, you can recover the full Hamiltonian. Okay, and future work is that, so through this study, we have learned that the surface with infinite genus is quite important, plays a quite important role in this phenomena. So then we wish to ask what kind of infinite genus surface appears in the setup. And also we wish to know it is consistent or not. Okay, and let me make a comment on these papers. So actually we can see a similar behavior of the Hartle-Hawking wave functions in the Levy theory, precisely speaking, C equals 1 Levy gravity. And if you are interested in, please look at these papers. These are quite, I think, interesting. So I think that's all. Thank you very much.
Okay, thank you very much for this interesting talk. We have time for questions. Are there any questions? Comments or?
So I have a question.
Okay, go ahead.
Yes.
So your result tells that if you have infinitely many wormholes, then the size of the universe is infinite.
Yes, the average size is
So-
fixed
so-
by the cosmological constant.
So does it tell that the universe does not have any wormhole because the observational size of the universe is finite?
Well,
So
the
does it
expectation
indicate that there are no wormholes?
no, I don't think so.
Okay.
You mean in the four-dimensional real case?
Yeah.
Well, this is a very simplified setup under the two-dimensional case, so I
see.
think I cannot say about the
okay.
real. Sorry.
Okay.
I have also a very naive question. You
Yeah.
started the talk by dividing up in two approaches, the EDT and the CDT, the
Yes.
Euclidean and the CDT. And that will relate to Liouville. But is there anything to say about that approach? Are there similar results, or is that a completely different story?
Exactly. So in the case of EDT, if you take the quantum limit, we can have the Liouville gravity. And in the Liouville gravity case, this one, for instance,
That is that one. Okay, see that.
Yeah,
the one
C
you
equals
mentioned, yeah.
1, yeah, we can have the similar behaviors. So the wave function starts oscillating and decays with some power. But we have the different Hamiltonian, but the behavior of this Hartle-Hawking function is very similar. So I think this is quite interesting. So this has been shown in this paper, Bertios and Papadoulaki in 2020.
And what would be your obstruction? Suppose you would like to go to do this in other than 2 dimensions. What would be immediately the difficult thing to do? Where did you use in the most strong way that you are in 2 dimensions?
In a higher dimensional case, we didn't have the analytic way to compute this, to introduce wormholes and baby universes. So
it would be very difficult then. Yeah.
Well, yes, but there are some formulations in CDT, in 3D CDT, based on the matrix model, but it is not a full expression, so I think we cannot use that. So we have the, I think we need to have the new idea to consider the wormholes and baby universes in the real setup, the more higher dimensional case.
Mm-hmm.
But I think at least in 2 dimensions, we can do that non-perturbatively based on the analytic method. I think this is the interesting thing.
Okay, are there any other questions? If not, let's thank the speaker for this very nice presentation.
Thank you very much.